Hello students, today we will understand what is a normal force, right? And this is a very important concept and we need to understand it, and as I said, we'll understand it clearly, very clearly, right? Okay, so let's imagine a block of ice, and I'm going to imagine it as resting on a frozen lake. Okay, so that means ice on ice, right? So it's a frozen lake, and on that frozen lake I'm imagining block of ice. There is a reason why we imagine ice. So this is the frozen lake, and I'm imagining another block of ice as well. So this block of ice is stationary and this block of ice is moving, and it's moving at a constant velocity of 5 meters per second. Let's say it's moving, and this block is stationary. So as I said, this is ice, this is ice, and this is also ice. And the reason why I'm choosing ice over ice is that I want to get rid of frictional force. So we can assume friction to be zero, friction between the surfaces that is making contact. So at this point I can assume it to be zero when I'm considering ice sliding on ice, right? That's the reason, that's the only reason why, because we'll bring in friction later. Okay, so you have this ice, it will have certain weight. Okay, so let's say its mass is 10 kg. Its mass is 10 kg. Now, always we are going to, in this video, you need to always remember that the relationship that we are invoking comes from Newton's second law, and that is sigma F is equal to 0. Sigma F is F net force. So I'm so sorry, very sorry. Sigma F is equal to mass into acceleration. That's what I meant, right? Sigma F is equal to mass into acceleration, or F net. Sigma F is F net. F net is equal to mass into acceleration. So this is what we are always invoking when we are dealing all the cases, these two and the cases hereafter that will follow. Okay, so this is stationary, meaning what? It has got zero velocity. It has got zero velocity. So if we invoke second law, Newton's second law, sigma F is equal to mass into acceleration. Velocity is zero, that means it's constant velocity but zero, that means acceleration is zero, which means net force, right? Net force. So we are saying F net is equal to sigma F is nothing but F net is equal to mass into acceleration. If velocity is zero, that means a constant velocity having zero value, magnitude. So F net is zero, right? F net is zero. Fine. So if F net is zero, now, so the body has got zero net force. The body has got weight, right? It has got certain mass. So that would be, that is acting downward. The weight of the body, which is equal to m into g, the gravitational acceleration is m into g, so that's acting downwards, right? So the weight of the body is acting downward, right? Acting downward. Now if the weight of the body, which is equal to m into g, is acting downward, and we are saying that net force has to be zero, and this is vertical downward force, it means that there has to be an upward force which cancels out this mg, right? Which cancels out this mg. So the upward force here is normal force, Fm, and that also has to be mg. That also has to be mg, otherwise this will not be cancelled. Now why this normal force exactly, you can understand this normal force also getting it at taking a microscopic view. How these bodies pressing and there are molecules, how they are resisting the negatively charged particles, pushing up negatively charged particles. We can, that's a microscopic understanding, but we don't have to get into that. We are interested in the macroscopic effect. The macroscopic effect is a normal force, and the normal force has to be exactly equal to mg, right? So this is one understanding. We are going to add more complications to this. Now let's consider this body. This body is moving at a constant velocity, right? Now when it is moving at a constant velocity, what will be the net force on it? What will be the net force on it? Obviously the net force is zero, because the body which is moving at constant velocity will have acceleration equal to zero. So net force has to be zero, right? Net force has to be zero. So it means it's moving in this direction. So net force in this direction is zero, right? And so in the sense that there is no friction, because I am considering ice over ice. So the body is moving, there is no force acting on it in horizontal direction. It is moving at constant velocity. There is no resistance. Of course, there will be if you are neglecting air resistance. So that's horizontal. What about vertical? Again, the body has got mass, right? Consider 10 kg of mass. Mass is equal to 10 kg, right? And the weight of this body acting downwards is m into g, that is 10 into 9.8, which is equal to 98 newtons. Same was here, 98 newtons, because I considered mass. Okay, so that is acting downward. And then we are saying that, see, imagine if there were no force acting upward cancelling this, what would have happened? The body would have accelerated in downward direction. Same here, I should have mentioned it. If there were no force acting upward, the body would pierce through the ice, accelerate through the ice, right? It's not happening. That means there is a balancing force, and that is normal force. So here also, body is moving, but body is not falling down because of its weight. So what is holding it at that position? It is the normal force, right? Normal force, Fm, and that also has to be equal to mg. Okay, that has to be equal to mg. Now we are going to add something more to this. So this is our understanding of normal force. But now, what if the body, this body, I am considering the case body is stationary, body is moving horizontally, right? Now we will consider case, what if the body is moving up and down, right? And we can consider the body moving up at constant velocity, right? Or we can say body is moving, accelerating, or we can say the body is moving down, right? And accelerating downward. So we can consider all these cases. And will the normal force change, or will it remain same?